Last class we had a discussion on the bulk micromachining of silicon. Today we will discuss on surface micromachining of silicon as well as quartz micromachining. As I told in my lecture on MEMS materials that quartz is also an important MEMS material. Lot of sensors are fabricated using the quartz because it is a very good piezoelectric material. So, if you use quartz in MEMS sensor, you have to have some technology on micromachining of quartz. So, that part also I will discuss in today's lecture. Now, surface micromachining is a direct extension of semiconductor manufacturing technology. Direct extension means it is coming from the normal etching which is used in VLSI processing. Bulk micromachining is not a direct extension, because in normal VLSI process do not require the etching up to 300 micron, 400 or 500 micrometer. But surface micromachining, here etching is in the range of few microns, 1 micron or 2 micron, in some cases maybe 500 angstrom also. So, that is why they mentioned that the surface micromachining phenomena is a direct extension of semiconductor manufacturing process, because the etching depth are more or less same as the VLSI process. Next point is it can manufacture devices an order of magnitude smaller than bulk micromachining on the order of 50 to 100 micrometer. So, where that means here the order the manufacturing devices you can make much smaller, one order smaller in dimension. The reason is if you go for higher etching, higher depth etching, so then automatically there are some slant portion will be there, which is not etching 1 like that, pyramidal structure. So, for that you have to allow certain space. But if you go for very small amount of etching in the range of say 2 micron or 3 micron, so that much space you do not have to spend in the silicon surface. So, in that way you can reduce the complete area of device if you go for surface micromachining technology. Okay. Next point is uses same wafer surface microelectronics. That means same wafer surface microelectronics means, so wherever you are on the same surface you are making microelectronic devices as well as the MEMS sensors. That means you are going to use same wafer surface for making the structure as well as the microelectronic device, means transistor, diodes, etc. That means it is highly compatible with the IC process, because it is surface micromachining, which is mentioned in the following point also. It enables integration of microelectronic and micromechanical components, because everything on the surface, your devices circuit is also on the surface. So, the mechanical structure is also on the surface. So, is a very easily you can integrate these mechanical parts as well as the electronic or microelectronic circuit part, because both are lying on the surface without any problem. It does not mean that in bulk micromachining you cannot integrate, you can do it, but with little bit more trouble you have to face there, because in case of some cases of bulk micromachining structure are a very uneven surface, where directly interconnection of lines, interconnect lines from the ICs and the mechanical devices cannot run so much depth, which is of the order of 300 micrometer or 400 micrometer, some cases say 200 micrometer also. So, that is why we call that surface micromachining process is highly compatible with VLSI normal process. That means, here smart sensor, basically sensor and signal conditioning circuit can be integrated very easily, which is not that much easy in case of bulk micromachining. And in surface micromachining process, the key is the use of a sacrificial layer. it is mentioned here. You can see this is sacrificial layer, means this is very important here, sacrificial layer. The key is the use of sacrificial layer in case of the surface micromachining process. So, I will discuss in detail what is the sacrificial layer, what is the structural layer. There are two kind of layer we use in case of surface micromachining, structural and sacrificial layer. Silicon dioxide or photoresist are usually used as sacrificial layer. There are other also, but the silicon dioxide and the photoresist are very popular material as sacrificial layer. Okay. Now, surface micromachining, here you can see some diagram which explain how it can be, it can go for, we can go for surface micromachining structures. It is basically based on depositing and etching structural and sacrificial films. After deposition of thin film, sacrificial layer is etched away, leaving a completely assembled microstructure. Maximum possible thickness of the microstructure is limited to that of the deposited film. So, now let me little bit explain based on this figure. So, now here this is the substrate which is silicon, this substrate may be silicon. Now, on silicon substrate, first the sacrificial layer which is silicon dioxide, that is either it is grown or deposited. Then you pattern sacrificial oxide, that means here you will get, after patterning this case you will get like that, because this is something like this, you will get this is silicon, okay, and this is oxide, silicon dioxide you pattern. Now, you deposit here this polysilicon layer, that polysilicon will be the structural layer. Now, you pattern polysilicon, because when you deposit it will be deposited like this. This is the polysilicon. Okay. Now, after that you just using photolithography you pattern it. If you pattern, it will be like that. Now, in the put whole thing in acid bath. If you put in acid bath which can etch the sacrificial oxide, so that you see oxide is not a crystal, that means that etching is here is isotropic etching. If you put in acid bath, so it is not direction dependency like silicon etching, means 1 1 1 0 0 or 1 1 1 or 1 1 0, this anisotropy of etching depend crystallographic plane orientation anisotropic etching, that point, that those points are not coming into picture in this particular case, because you are etching silicon dioxide whose etching solution is hydrofluoric buffer hydrofluoric acid. So, now if you etch the sacrificial oxide, that is basically the isotropic etching. So, that means it will etch from top also, and then after etching, complete etching this particular location here and here, then it will etch in this direction, it will go here, it will go here like that. So, that means wherever the oxide, complete oxide is removed, then what will be there? It will be complete hang. Because it is isotropic etching, laterally it will go, and your selective etching you are using, that is buffer hydrofluoric acid, that will not etch silicon, underlying silicon. So, it will go in this direction, and again it will go in this direction, it is go in the other side also, like that. In this way the complete oxide will remove, and that this structure will hang. So, that is basically the surface micromachining. In the next view graph, I will show you in detail with respect to the mask how the surface micromachining process the process steps basically one by one. Now, this is the cross section schematic process, the diagram, 2-dimensional process of the surface micromachining. What I just told you there, you can see the first one is the silicon substrate, first step, then you deposit silicon nitride, because in many cases the structural layer may rest not on silicon, but on some insulating layer, because if you rest the earlier diagram which I showed, that is resting on silicon. Silicon is not an insulating layer, this is semiconducting material. So, semiconductor material means that the hanging structure what you are making, that will have some contact, semiconductor to polysilicon contact will be there. If I do not want it, if you want the isolated some free structure, then we have to structure or we have to fabricate that one on some insulating layer. That is the reason why in this diagram, first on silicon we have deposited silicon nitride. You can see here this greenish color, that is silicon nitride. This is silicon nitride here. After silicon nitride is deposited, that is basically known as isolation layer, which isolates the substrate and the structure, that is why known as isolation layer. Now, we are coming to the third diagram, which is the silicon dioxide deposition and then patterning. Silicon dioxide deposition and patterning, which is a sacrificial layer. Sacrificial layer is always lateron removed. So, the silicon dioxide is deposited, then by using photolithography technique we pattern here, we made a hole in this particular location, a hole is made here by photolithography technique. Now, coming to this step, now we deposit polysilicon. Polysilicon is deposited here. Now, if you deposit polysilicon, it will not be conformal, because here some groups are there. So, automatically here it will go, the shape will not be exactly plane on the top of the surface, it will be something like that. Okay. After that, you pattern polysilicon, just I showed you in earlier view graph, pattern polysilicon using the lithography technique. Then you go for etching that silicon dioxide SiO2, which is this is SiO2, and that we remove completely, and this is the hanging structure on nitride. So, it is this is isolated from the silicon substrate. This is basically the silicon. On silicon substrate, this is basically silicon nitride Si3N4. Now, on Si3N4 you are just structuring that the polysilicon, you can say cantilever beam, you can make it. This is surface micromachining process. Now, this is another view graph, you can see the 3D process flow. So, earlier view graph is a 2D process flow, and this is 3-dimensional view is given. So, that you will have good conception regarding how the surface micromachining is going on. So, 3D view, that means similar to that. Here again there is no insulating layer is there, only on semiconductor the free hanging cantilever beam. How can you fabricate? It is shown here in the first diagram. You can see here that is this is basically on the deposit and pattern oxide, the similar. Earlier is a 2D view, it is a 3D view, that is the difference. So, you oxide pattern, then you oxide pattern is shown is a cross sectional also, what you have seen, say this is a 10 micrometer, this oxide, this is, it looks like this. If you see the cross section and if you do the 3D view, it looks like that. Then you polysilicon, you deposited and pattern, deposit and pattern poly. So, you will get polysilicon layer and pattern like that. Now, you remove this, the silicon substrate, this is known as anchor. Anchor means when it is fixed with the substrate, and you etch sacrificial layer, it looks like this. Okay. Very simply, the 3D you will have some clear picture view, clear idea how the complete thing is going on. Now, so thus after that the process of making structures using surface micromachining, we can see the main advantage of this particular method is the easy integration with integrated circuit components, because here the whole thing lies on the surface and over little thickness depth. Okay. So, that is the main advantage of the surface micromachining process, and I also told you this is a structure is one order smaller than the bulk micromachining. Now, what are the common approaches to the making of micro electromechanical system devices using surface micromachining? One is sacrificial layer technology. Now, here in this particular case, the sacrificial layer technology, just now I discussed how it can be done. Second is wet anisotropic etching. Some cases we use isotropic etching also, because when we want etching from the side, so it is vertical edge as well as lateral edge. So, that is isotropic. So, the wet etching is much favored in making surface micromachine devices compared to the RIB or RIE, because when you need isotropic, then RIE is cannot give, you have to go for ion milling technique or the plasma etching technique, which is isotropic in dry, but in liquid, normal liquid etchants are mostly the isotropic etchants. And third one is a plasma etching. Plasma etching, as I just now I told, plasma etching or ion milling etching, these are isotropic in nature, but if you use reactive ion beam etching, those are mostly anisotropic. You cannot get the isotropic property there. So, normally if you want to remove some of the layer film below certain layer, you have to go for the lateral etching also, then best choice is plasma etching or wet etching. Now, here is a integration of sensor and IC in surface micromachining, you can see here. So, this is a complete picture of one MEMS where micromechanical system. So, devices as I are all integrated on the surface of the silicon, as I just now few minutes back I told you. So, here highly possible integration of the components and circuits and micromechanical structures. So, here this device some cross section is shown here. So, basically here you can see say the devices, say NPN transistors. So, NMOS device, and then it is connected with this layer, the sensor area, and the sensor area here how the sensor looks like, it is also shown here. So, in the middle portion in this particular location you can get this sensor area is here, and the peripheral they are using the other this here and in this direction all are the circuits, and some cross section how it can couple together the BJT, the emitter base and collector, that is also there. And obviously, the technology is not as simple as your normal transistor fabrication process, because here you have to have some compatibility study, somewhere you have to forego some of your requirements. So, in that case some compromise has to be made in process technology, complete process technology, and the sensor area how this is sacrificial oxide is shown here, how it is removed, and just like that cross section if you see the sensor area can be floating, some floating structure you can make like that by using surface micromachining. At the same time you are making devices here. So, the integration of sensors and ICs are shown in this diagram. Now, then in a nutshell we can say what are the key processing steps. First step is the deposition and patterning of a sacrificial silicon dioxide layer on the substrate. Next step is deposition and definition of a polysilicon film. If you remember the cross section diagram, just you can see after the sacrificial patterning we are depositing the polysilicon film. Then removal of the sacrificial oxide by lateral etching in hydrofluoric acid. If you need select hydrofluoric acid is a choiceable thing if you do it on insulating layer. If you go for etching of silicon dioxide on silicon nitride, then there is no problem with hydrofluoric acid. You do not need selectivity with silicon, but in some application if you want to make this structure on silicon, then you have to go for buffer hydrofluoric acid, because BHF does not attack silicon, it will attack only silicon dioxide. Okay. Now, etching away the oxide underneath the polysilicon structure, here we refer to polysilicon and silicon dioxide as the structural and sacrificial materials respectively. Now, the polysilicon cantilever using surface micromachining, there are two methods, one is known as one mask process, other is known as a two mask process. So, in some case you need two masks. What I discussed in earlier view graphs, that require two masks. One you patterning the the sacrificial oxide one mask, then you are patterning the structural layer another mask. That means, sacrificial layer patterning mask and structural layer patterning mask, when you use both, then it is known as the 2 mask process. On the other hand, you can go for only 1 mask process also, but with some limitation. That is difference is shown here. In the left side is the 1 mask process, you see silicon dioxide is grown, then the structural layer is deposited, and then after that the structural layer is patterned. This is the pattern like that, this is the pattern of the structural layer, this is the pattern of the structural layer here. So, now if you pattern that structural layer, then it looks like this. Then what they did is just go for the etching. What etching? Silicon dioxide etching. Now, here you see I told some limitation. What are the limitation? Limitation is that the beam is floating here, it is supported on silicon dioxide, but if you go for 2 mask process, that this region is also made of the structural material. Just side by side you see it. Here is the first mask, you have anchor definition is the first mask in the structural layer, then you deposit polysilicon, then you remove the structural layer, you are getting this structure. Now, if you compare this and along with this, then what you will get? You will get here. So, you see here this material and this material both are same, but here this one and this one are different. On the other hand, another limitation, if you go for longer etching, this particular point may also etched, the anchor region may also etched. So, that means you are making a simple process by using only 1 mask at the cost of some limitations. So, these limitations are these one. So, here another point is there, this kind of the surface micromachining structure, for example, if the surface area is very large, for example, instead of that if you want to make like this. So, this instead of this one, if you get larger area, then what will happen? Everything is etched from the side. So, that side etching gradually will reduce with time. So, if it is a very small area, so immediately with a small amount of time it floats, but over a larger area, complete removal of the underlying layer, it will take lot of time, and then the problems of surface stiction will come into the picture. If the larger area, longer length, even is a narrower width and long beam if you want to make, then surface stiction problem, which I will again address after few minutes in the same lecture, then we will find those are some added hazards or added problems in case of surface micromachining. But if you go for 2 masks, if you use another mask also, then the total thing is easy, and both things are with polysilicon, and then the removal of this particular layer with longer etching, that problem is also not there. This layer means oxide layer. Okay. Now, just I was mentioning regarding the problems of surface micromachining. One problem is surface stiction, and that surface stiction you can just see here. So, this is the surface stiction is mentioned here, and in figure you can see. So, when you are, this is a particularly basically the you see the top layer is a structural layer, this is a structural layer, structure, and this bottom one is a sacrificial. Okay. Now, if you go on etching, so here long beam, so there is a possibility you see here because of the surface tension of the liquid etchant. So, if it is a small area, this region will stick with that. You can see this particular portion sticking, that in surface micromachining long beams will stick here, and as a result of which it may break here. So, that problem is known as surface stiction. and the surface tension of the water under the structures pulls them down to the surface of the surface of the wafer and causes them to adhere permanently to the wafer surface. It accounts for 90% of structural failure. It accounts for 90% of the structural failure. That is the major problem of surface micromachining. There are certain solutions also in order to get rid of that kind of surface stiction. And nowadays, there are two solutions people thought about it. One is in the etching solution, you add some chemical, so that the surface tension will be less and less. That is one, because it is basically because of the surface tension. The second one, you modify the structure at the mask level, so that you can create some small bumps in some of the location, and which will prevent bending down the structure. That is shown in the next view graph. Here you can see bumps or dimples. Bumps or dimples are made. This is one bump, this is one bumps, small bumps if you made. So, when you are etching, so if you make like that, you go on etching. So, this kind of thing will help you to stop breaking at that point and that point. Sometime some other methods to prevent this sort of this surface stiction are freeze drying, which is sublimation of the final rinsing solution. This basically comes from the when you are drying, because when it is a liquid in water. So, when water is removed, then it will drag, it will pull the small thin beam to the surface. But if that rinsing and drying, if you do by sublimation method, then that problem, for example, if you can do it completely in alcohol. So, alcohol will evaporate, and that problem, that surface tension of that is less compared to the water. So, similar a lot of R&D is going on in this direction, how to remove the surface stiction problem. Use of integrated polymer support structure during release of etching and assing of PR. Some support structure, assing of PR means this is a photoresist assing, that is in case of your dry processing, plasma processing, there you use the assing technique, means the burn, photoresist is burned and removed. Okay. So, or you can use some of small polymer support structure like this is mentioned here. So, in order to prevent breaking of the structures. Okay. So, these are some of the solutions of the surface micromachining. Now, using that surface micromachining technology, I will now discuss on few structures fabrication, how it can be done, how it can be processed. So, that details 2-3 examples I will give. First example I have chosen is a freestanding polysilicon beam. Freestanding polysilicon beam. This is very simple, because it is a direct extension of the surface micromachining process what you have just now we have discussed. So, freestanding polysilicon cantilever beam anchored to a silicon substrate via an insulating nitride. Freestanding word is mentioned here. That means, this cantilever stand freely without breaking. That means, if you apply sudden jerk or sudden stress on that particular beam, it will not break. That is why here one small modification has been done in the thing, which is a dimple. You can see here this particular point was not mentioned earlier, here and here. dimple structure. So, here then what are the steps? First you take the silicon, this is silicon, this is silicon. Now, on silicon you are LPCVD silicon nitride of thickness on which the freestanding beam is to rest is deposited. This is the silicon nitride Si3N4. Okay, Si3N4 is there. Then after that you pattern this Si3N4, not only the anchor region, but here some dimple is made, you see that dimple will help, what help? So, it will not allow the structure to break during the surface stiction problem, because some dimple is made here, or not surface stiction, basically here if you certain jerk if you give or certain pressure you put on the freestanding beam, it should support here. So, it should not break. So, that is why here also you made some groove and here complete removal of the nitride. Then you deposit the sacrificial oxide in CVD technique on silicon nitride. On silicon nitride only CVD is the only way to get the layer. Why? Because there you cannot grow thermal oxide, either you go to CVD is the external reaction and the deposition of oxide, or you can go for sputter deposition, is not it. So, then you go for the basically lithography pattern such that the oxide thickness is equal to the height above nitride layer surface of the freestanding beam. So, now this is lithography pattern, deposition of polysilicon by LPCVD. This is the bottom was the nitride, bottom was the nitride, you can see nitride, then this is a silicon dioxide, then you are getting this is polysilicon. This one polysilicon, and then you pattern it, then remove this layer which is oxide layer, remove it, and you are getting light. Lateral etching of sacrificial silicon dioxide, freestanding beam is finally created. Okay. So, step by step if you go like this, you can get this structure which you are aiming for. Okay. So, now let us now compare on this two method of micromachining. One is a bulk micromachining and surface micromachining. Advantage and disadvantage of both the process are mentioned in this view graph. So, advantage for bulk is, it is a well established technology since 1960, is a rugged structure, withstand vibration and shock, bulk micromachining structure, but disadvantage is a large die areas that give it high cost, die size will be more, because its size is one order more than the surface micromachining structure. Another advantage, large mass or area you are going to use. Disadvantage is not fully integrated with the IC process. This large mass and area you can use. Why I call it an advantage? Large mass or large area must be in disadvantage, but here this point is, this particular point is put in favor of the bulk micro, because some of the devices you require heavy mass, large area, heavy mass. Those are mainly in case of inertial sensors. One example is there, the acceleration sensor. So, there you need the proof mass more heavy, so that sensitivity will be more. So, that is why in some cases large mass or large area is advantageous compared to other. So, but at the same time it is not fully integrated with the IC process. Well characterized material silicon in case of bulk, limited structural geometry possible, but in surface micromachining advantages are uses several materials and allows for new applications. relatively new, since 1980 it is there, it is now from 1960, it is from 1980. Small die area, that makes it cheaper, just comparison with that and this. Less rugged with respect to shock and vibration, fits well within IC process, the advantage in surface micromachining. Disadvantage, small mass area, reduce sensitivity. Just now I told you that sensitivity will be more if you increase the probe mass weight more heavy. So, since a small mass area, its sensitivity will be less. Wider range of structural geometry in surface micromachining, it is possible. Some of the materials are not well understood in case of surface micromachine, particularly ceramic and say composite materials. If you go for microstructuring in surface micromachining, some of their materials are not fully known, characterized. Okay. So, these are a comparison of bulk and surface micromachining process. Now, I will discuss on again some example of the surface micromachine structure. One example now I will discuss, that is silicon condenser microphone. This is one important application of micromachine devices, is a condenser microphone. Small microphone, miniature microphone is the demand nowadays. So, that miniature microphone can easily be formed using surface micromachining technology, and how it is made, that is shown here. You can see here, in this particular case we have used silicon nitride as a structural layer and aluminum as a sacrificial layer. The condenser microphone basic principle, you know, you have to have a diaphragm. On the diaphragm there is a electrode, metal electrode. So, that diaphragm, when it moves depending on the acoustic signal, so in presence of some magnetic field, so some signal will be generated, electrical signal will be generated. That means, a diaphragm when moves, vibrates in presence of a magnetic field, then it generates some electrical signal, and that vibration of the diaphragm or membrane frame diaphragm depends on the acoustic energy. If you say something in front of that condenser microphone, so then it will vibrate. So, how this kind of thing is made using the MEMS technology. Now, here we use the silicon nitride as a structural layer, aluminum as sacrificial layer. Now, you see what is being made. First, a silicon wafer is taken, then you oxidize the silicon wafer. So, you can see the white region, this region and this region here. Okay. These are the thin layer of silicon dioxide which is shown here. After that, growth of silicon, thermal oxide, back side and front side. Back side is 1.8 micrometer and front side is only 0.4 micrometer of silicon wafer. Etch of backside square window, you see you are etching backside square window here, etch of backside square window. Deposition of aluminum sacrificial layer. After that, what you have done? You have deposited, first you did the etching of backside here, then you deposited aluminum. This is the aluminum, this is the aluminum. Then you pattern, 1 micron aluminum is deposited here, 1 micron aluminum. Then this aluminum you pattern, then you deposit PCVD silicon nitride, Si3N4 1.3 micron. So, that means, first what you did, silicon dioxide is grown from top and bottom, then window is opened by lithography technique bottom, then on the top you deposit aluminum of 1 micron thickness, then pattern this aluminum, then on this patterned aluminum you deposit PCVD silicon nitride. After that, on PCVD silicon nitride we deposited titanium gold as the electrode. You see, the anisotropic KOH etch from the back side has been done. After that, and you will get this kind of V group. Silicon dioxide in this particular location here and here will act as the H stop layer here, and this silicon dioxide here is also working at H stop layer, because silicon will be etched from backside here and here. Okay. And after etching, it will face silicon dioxide, then it will be stopped there. So, that means, in the structure you are getting a membrane like this. After that, this silicon dioxide H stop layer has been removed, and then this aluminum is etched. If you etch the aluminum, and that aluminum etching solution is the phosphoric H3PO4, HNO3, acetic acid and water at 50 degree centigrade, you will etch the aluminum, and before aluminum etching you just get that the gold film, and before gold small amount of titanium has been deposited for proper adhesion of the gold with the PECVD nitride. This is PECVD nitride, this is Si3N4, this one. Now, they are titanium gold layer, and then if you etch this complete aluminum, that is why I told that aluminum will be the sacrificial layer, then you will get this the diaphragm, and this is the acoustic hole, and this is filled with the air. Now, just like a microphone, this is one electrode which is a titanium gold, basically gold electrode. Now, depending on your here, if you speak something or some acoustic signal is applied in this hole, then accordingly it will vibrate. So, this electrode will move, and below that this nitride is given in order to have a stability, structural stability. Only this gold film will not be stable at all. Basically, the diaphragm is made of silicon nitride. Silicon nitride is the diaphragm, and gold titanium is the electrode. Now, here if it vibrates and whole thing you put it in a magnetic field, automatically the signal will be there, is not it. So, that is the way how you can make a silicon condenser microphone in a very small area, it is a very miniature form, and which can easily be integrated in silicon in a just the conditioning circuit and this condenser microphone integrated together, is not it. So, which was not possible in earlier. Now, this kind of condenser microphone, if you can integrate along with the circuit itself, so then it will be a very good thing. Okay. Now, another example I will just give you, that is silicon micro Velcro. How can you make silicon micro Velcro using the micromachining technology? And in this particular case, we take help of both isotropic etching and anisotropic etching, both are used. Let us see how it is done. Micro Velcro is basically one application is button snap or zipper. You see, button snap or a zipper, that is the application of the micro Velcro. So, in your zipper, the technology is basically is a Velcro. Two micro Velcro is in opposite way, they are joined together, that is your zipper. So, a regular array of microstructure that can be used as a zipper in 2D configuration. The structure behave like the well known Velcro material. What is the step? You can see the diagram here. So, here first silicon substrate, then silicon dioxide is grown, that can be done with thermal growth, then photoresist coating and patterning the photoresist. Okay. So, this step A is over. Now, after that you remove the silicon dioxide, then using the silicon dioxide as a mask material you go for etching of silicon. That silicon etching, that is silicon etch, and which is what is that? That is anisotropic etching. The silicon etching is anisotropic here, because your this direction is 100 direction is etching, but this surface is not etching, which is exposed and maybe 111. Okay. Now, that means here you are using anisotropic etching. After that you clean whole thing, then you again grow for silicon dioxide second time. First time silicon dioxide is grown here, the second silicon dioxide grown. So, when you grow silicon dioxide here, so it will be grown over the whole thing, here, 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 whole thing. Now, you sometime you dip it, then what will happen? If you etch after growth directly, if you go for etching without any masking etc. So, in this particular position thickness is small and here it is large, and here is also the side relatively large. So, now by suitable technique you just open that silicon dioxide here. That you can do for do by using masking also. Then you have to need another mask, so that only this portion silicon dioxide is etched, or if there is a thickness variation of silicon dioxide, where because this is already grouped in a group region, if it is a small thickness offside and this portion thickness is large, because it is exposed more and more the oxidant molecules, then growth rate will be more there, but since narrow groove here growth rate will be less. That also you can use, or you can use some mask also, so that later on you remove the oxide here, here and here, then go for silicon etching. So, now here the silicon etching is done, and that silicon etching is isotropic, because it is etching here, then it is going there, it is etching below, then it is going there, here and it is going there, here and then going there. So, that means in all direction it is etching, that is isotropic. That means once you used here silicon anisotropic etching, but here you are using silicon isotropic etching. So, lateral and vertical in all direction is etching equal. So, because of that you are getting this structure, you are getting this structure, you are getting this structure, you are getting this structure. Now, similar structure to make another, now you press it, similar structure another, now you invert it and press it. So, then what will you see? It will just push and the whole thing will drop on here, another will be here. So, it will just like a zipper. That is known as the micro velcro, and just like this thing, once you get this, then you just you can get for interlocking of this is important. Second QH etch for 3 minutes and then isotropic silicon etch 2 minutes. So, first 2 minutes for QH and then isotropic silicon etching for another 2 minutes. So, then you will get this structure. Then the vertical clearance as well as lateral clearance, so that you can interlock two structure and closely, because the lateral undercut there. So, they can push it, they can cross it, put it here and they can do like that. So, this is the one kind of structure which microstructure we can make, which can easily be made using the micro velcro technique. Okay. So, now let me now discuss something on the quartz micromachining. Micromachining of quartz. Why quartz? Quartz is a unique semiconductor material for microelectronics, VLSI, MEMS and integrated sensors. It is basically quartz is a silicon dioxide insulator crystal, because this is silicon dioxide, but in crystallographic form. Silicon oxide quartz is crystallographic form, but normally silicon dioxide which is used for masking, that is amorphous in nature, but quartz is a crystal material. It will have piezoelectric property, low temperature coefficient, high mechanical strength, thermal stability is very high, it is radiation hard, unique oscillator for crystal, and you can make short devices also using quartz, and special MEMS, MOEMs you can make it, micro optoelectromechanical system, integrated optics devices you can make. Now, if you compare the silicon and quartz, then the properties are like this. Silicon resistivity in that range and quartz is 10 to the power 15, that means it is much more insulating material, strong insulating material. Duality constant were 12, here 4.5, density is almost equal, and Young's modulus, bending strength and tensile strength are compared in this table. These are the comparison of the mechanical properties of silicon and quartz. What kind of structure we normally make out of the quartz? We make cantilever beams, miniature tuning forks, triple beams, dual and double ended tuning forks, membranes and flexures. This kind of structures has lot of application in quartz MEMS or MOEMs. What kind of application? Lot of application I mentioned. What are the applications? One is known to all, that is oscillator structure. Since it is a piezoelectric material, you can get very good crystal oscillator, and for that if you want to shape, it can be done by micromachining, and you know the resonance frequency depend on the structure of the piezoelectric material. Dimension structure, that will give you the resonance frequency, as well as if you make with that some tuned circuit, its Q value will depend on how you make the structure, what is the dimension of the microstructure. So, high frequency stability is there. Accelerometers, gyros can be made out of quartz. Actuators, because it is a piezoelectric material, if you apply electric field, it can vibrate with certain frequency. So, vibrators, vibrating, if it vibrates, if some optical signal is incident on that quartz vibrating, then you can make vibrating mirror also out of that. Optical choppers you can make, and most important property of the quartz, because of which it is getting much more importance, that is it is temperature insensitive and radiation hard. These 2 points are very, very important, because like piezoresistive sensor, this is highly dependent on temperature. Quartz sensor is temperature insensitive. Piezoelectric property does not change with temperature. It is very important. And another important point is the radiation hard, because if you use sensor in space, so you have to look into the matter radiation hardness, because in space lot of alpha ray, beta ray, gamma rays are there, in addition to the ultraviolet rays. So, those rays in case of silicon piezo resistive material can produce lot of carriers, electrons and holes or something like that. So, they will generate some current, radiation current because of the radiation, but that possibility is not there in case of quartz. That is why it is a radiation hard, rad hard device can be made using quartz. Okay. So, these are the advantage, and if you go for quartz micromachining, then you have to go for certain steps. What are those? Standardization of anisotropic etching of single crystal quartz, standardized you have to do. Selection of proper masking material that can sustain prolonged etching in fluoride based solution, because all etching solutions of quartz are fluoride based. So, there you have to choose, you have to select certain mask which can withstand long standing exposure of the fluoride based solution. Third point is development and optimization of lithography process for micromachining of quartz, which requires double side alignment. Fourth point is the development and optimization of selective deposition of electrode materials at the sidewall of quartz micromachining structures through vacuum masking techniques. Because if you make a quartz sensor, not only in the top and bottom surface you metallize and get the electrode, it may require many cases the sidewall electrode. Sidewall you have to give the metal electrode to improve the Q value of the resonance structure. So, that sidewall electrode formation is not easy. For that you need a special kind of technique which is known as the vacuum masking technique, and that will help you to get sidewall electrode, as well as conventional techniques can be used for bottom and top side electrodes. Okay. Now, the anisotropic quartz etching, what are the materials you use? Chromium gold is used as a masking material, 300 angstrom chromium film, 3000 angstrom gold film, followed by patterning, it will get the masking material. Deep etching in HF based solution at various temperature through chromium gold pattern mask. Okay. What is then etching solution? Hydrofluoric based solution is the etching solution. 80% hydrofluoric acid at 80 degree centigrade is the first. However, large King's crystallographic facets appear at both x and y sections. So, some crystallographic facets will be created, and those facets will create some problem in your structure. Etching in saturated ammonium fluoride HF2 solution at 80 degree centigrade yields low etch rate and smaller kinks. So, this part of the quartz etching and how to get regular structure, that I will continue in my next lecture also. Thank you very much.